Hello everyone, welcome on this video lecture. And we are studying about the force. In the last video lecture, I have given you a homework based on the two force learning. One was gravitational, another was a normal reaction. This question is based on the normal reactions. And this is the arrangement that has been shown to us. And we need to find which option is correct as far as the normal reactions are concerned. So we need to see this rod separately, we need to see this sphere separately. Here the rod separately has been drawn. And let's say what this rod is going to get. Rod is going to get a normal reaction at A, normal reaction at B, because these are contact, normal reaction at C. So normal reaction is a contact force. It acts whenever there is a contact between two objects. Okay. So let's talk about that A point and check at this A option. Normal reaction, as we have talked about, it's always perpendicular to the contact surface. So this rod surface and this point, they are in contact. So this will be the contact surface. And perpendicular to this contact surface is going to be this line. So normal reaction must be along this line. This must be perpendicular to the rod at all the time, right? So in first option, it has not been shown perpendicular, rather it has been shown horizontal. So NA has been shown as horizontal, so this is not correct. It must be in the direction perpendicular to the rod. So this is incorrect graph or diagram. Let's come to the second part. Normal relation at A point has been shown perpendicularly. Yes, so the one condition of perpendicularly is true. Then another condition for normal relation was it has to be push effort. So this A point or this is fixed support must be pushing the rod up. So that means arrow should be in the upward direction. Yes, it is in the upward direction. This is how it can be shown. It can also be shown like this. It's okay. That means we know, because you can take a vector from here and put here. It's always true, right? Correct, you can say. But there will be one difference. When you plot like this, you will not be able to say that this is a pushing effort just by looking at it. So that appears as a pulling effort. So that's why we are drawing like this. But sometimes if you get like this, you also mark it as a correct, because that's as per the vector, this is a correct, right? So this A reaction is a correct. Now come to the B point. Again, it has to be perpendicular to the rod and perpendicular to the tangent. That means common tangent, you can say. So it has to be in perpendicular direction. We can also say this normal relation is along the common normal, because this is a common tangent, so this is going to be common normal, or we call it perpendicular. So this is perpendicular, yes, it has to be pushed. So this sphere must be pushing the rod. Yes, it is pushing the rod, so arrow is downside. So that's also correct. So both these normal relations are correct. Now let's come to the C point. At C point, the common tangent is going to be this. So common normal will be perpendicular. So normal relation has to be perpendicular at that point. Here it has to be perpendicular because the contact was this point of the rod, not the entire rod. So this was the common contact surface. So then it has to be perpendicular. It has to push effort. Yes. So it's meeting all the requirement, because this common contact surface is this perpendicular to the surface. So saying this normal relation is always perpendicular to the rod is wrong. It will be perpendicular to the rod if it is somewhere in between points. At terminal points, it may be at certain other angle, because it looks for the common contact surface, which is the surface of the another object. So B option is correct. Now come to the C option. We can check the C. What is wrong with C? At this point, again, this has to be perpendicular to this. That means toward the center. So it has to be toward the center. Yes, pushing. Yes. So NB is correctly shown. But what about D? D also has to be perpendicular to this surface. Tangents perpendicular to tangent. Yes. Or you can say common or normal. Normal always passes through the center. So it must pass through the center. Yes, it is passing through the center. But it should be pushing effort, because this wall should push this sphere. So this must have arrow in this direction. But the arrow has been shown opposite. So this became wrong. So you need to know why the C became wrong. It's just because this arrow was opposite. Now here you see this arrow have been corrected and it is toward the center. So that's perfect, because it's perpendicular to the tangent, and pushing effort, this wall is pushing this sphere, correct. But this time this NB has been shown wrong. because it has to be perpendicular to this tangent and toward the center, but it is horizontal. So this normal relation at B is shown wrongly, hence it is wrong. So finally answer becomes B option, which many of you have said that's a correct. Now let's move forward and talk about other forces. So we are learning basic detail about the forces, like forces, this is their vectors. So we need to know what the direction they carry, what the magnitude they carry. So, and also we talk about what is the point of action. In that sequence, this is the third one, the tension. This tension is on strings or threads or ropes. So generally, we will call them as strings. String has some assumptions, or we have some assumptions about this string. So this part we have talked about earlier as well, but still I'm going to explain it in short. Let's say this is a string, and this string is having a length A between A and B terminals. So we will assume its length remain constant. So we assume it to be having these two assumptions. First is that length is constant. Since length is constant, that means if you pull it, length is not going to increase. Later on you'll find length will increase, but in primary level we will be considering that length is not increasing. So it is inextensible. Inextensible. So that's the first assumption. That's the assumption. What is the second assumption? It's a massless. That means we will assume any string, any rope, any thread to be massless until and unless question says that it carries mass. If the question says it carries mass, of course, then we will drop this assumption and we will think about what that mass is and we will use it. Similarly, until and unless it says anything, we will assume it to be inextensible. If it says it is extensible, then we will be dropping this assumption as well and will be working with the extensible property. Extensible means length can change. Now, if this is a string and this string is being pulled, now we know the string you cannot push. You take a string and try to apply this force. So string is not capable of opposing this force. It will slack immediately, right? So that's why we are not going to study about this push force or this compressive force. Rather, we will be talking about those forces which tries to pull it apart. That means tries to increase the length. Now, if you are applying any force F on this, then you need to apply the same force in this in order to put it under tension. Put it under tension. Now, if it is massless, then no matter what happens, these forces has to be equal, because if you say them F1, if you say this F2, so net force you are going to write as F1 minus F2. Later on you are going to learn this net force is equal to mass into acceleration. Since it is massless, so mass will become 0. This is because the assumption is a massless, so that means F1 is always going to be equal to F2. Meaning is this, that for any massless string, the forces that you apply on the string at any point, they are equal. They are always equal. So if you apply any force here, it will be the same force acting over there. That means F1 equal to F2. And this is also called T. That's what it is called. It's called TT for tension. That means even if we think about any other point, maybe a point C over here, you will find C will be subjected by the same force F, or you can call T. So how you can see that? So you can draw the AC part separately and you can draw this CB part separately. If you draw these parts separately, then you will be identifying that if this is subjected by a force F, so there must be a force acting F, so that net force becomes 0. Why the net force has to be 0? Because it's a massless. Similarly, in this CB part, F must be acting like this to compensate for this, so that this branch is also, this part is also having same amount of net force, which is 0. Zero amount of net force is required. So this is AC and this is CB. Now this is what you are imagining what happens at B point. But if you what happened at the C point? If you place these 2 points together, then you'll find these forces will add up and they are equal and opposite forces, hence they will become 0. Whatever these internal forces are, these internal forces are known as tension. Now this tension is coming because of this external force. So that means whatever the external force you apply, the same force gets converted into tension. And this tension appears at all the points, not only at A point, not only at B point, but it at a C point as well. Now C could have been taken here, C could have been taken here. So you can take C point at any point in between these two AB points. That means tension acts at all the points. That tension is simply equal to the force that you apply. That means the force that you apply externally. And one more point we have understood, this external force acts equal in both the ends. Equal in both the ends. So this force is known as tension. Now you can see the direction of these forces. These forces are always along the string, always along the string. That means in a string you cannot apply force like this. So you will not get a force like this or maybe like this. You will always find along. This along point is trying to explain that what is the direction of this tension at any point. Or you can think of this tension is always a pull effort. It's always a pull effort. So it's a pull effort and acts along this string that will let to know the direction. So few important points that will be helpful to know the direction and magnitude I'm going to write over here. The first point, for a massless string, the tension at all the points has the same magnitude. So we can write with this assumption, this can be written as a tension at all the points, at all points of a string has same magnitude. Why we are calling as the same magnitude, not the same tension? The reason being, tension is a vector quantity and it has a direction, and direction may be different. Like you see at the C point, when you are considering this AC segment, then this F or T is pulling effort, right? If you look at this CB part, then it's also pulling effort, but both the directions are different. Since they are in different directions, so we cannot say they are the same vector, but yes, they have the same magnitude. So we are using the properties of vector. So at all points, tension remains the same, and that we have already used in constant relation, if you remember. Next point is about, let's write about the direction. This direction is going to be along this string at any point, and it will be always pulling effort. So direction is along the string and pulling effort, and it is pull effort, you got right. So pull effort means it's going to pull. That means tension can always pull things, it cannot push things. Unlike the normal reaction always pushes, normal reaction cannot pull it. So these are the differences. Next point we can write it as tension is of course a contact point. It's a contact force that acts as a contact point. That's a contact force, and point of action is contact point and acts at point of contact. So wherever this string makes a contact with object, at that point this tension force acts. It does not act at any other point, it acts only at the point of contact, and it's a pull effort, it's along the string, that's important term, and its value is same for all the points, same in magnitude. So these are the critical point, theoretical point that you need to keep in mind. And based on this, you can answer, that means you can answer the direction of tension, and you can draw the diagram. As far as the magnitude is concerned, magnitude is not fixed, it depends on the force that you are applying. So whatever the force that you apply, that becomes the tension. So we can say magnitude is equal to force applied or external force applied. External force applied. This is how you can get the magnitude, and this is point for direction, this is point of action, this is about the magnitude. in nutshell. So these points are important for tension. Now let's take an example. In that example, we will try to show the directions of these tensions. This example says draw the forces on blocks and pulley. And the two diagram. This is let's say first diagram A, and this is another diagram B. First of all, we need to see what this diagram is trying to say. Wherever this kind of shading is made, that means this is a fixed. So you need to read it as a fixed. And this is a fixed ceiling. From that ceiling, there is a string attached like this. And this string is fixed at the center of the pulley. And then this is a pulley. Pulley is also being considered as a massless. So whenever there is a pulley, you will consider it as a massless until and unless the mass of the pulley is given to you. What happens, there are two blocks. Let's call this is a block of mass m1. This is a block of mass m2. This block is connected by a string. That string passes over the pulley and connected to the m2 block, right? If m2 is bigger or higher, then you'll find this string, this will go downside, this will go upside. By common observation, you can think of that. Means you'll find this pulley is going to rotate like this. So this is going to the scenario, and we need to draw the forces on blocks and pulleys. So let's say I'm writing this m1 block, or you want to see this m1 block separately. What happens with this m1 block? This m1 block. So that means what are the forces that are going to act on this m1 block? We are basically bothering about the forces. So this is m1. Can we think of what are the forces? So how we are going to think, you are going to learn over here. First of all, we will think about what are the non-contact forces. So in non-contact forces, there is one force called gravity that is important for us. It acts at the center point. It acts vertically downside. So this force is the one that you need to show. This is a non-contact force. It is going to have a magnitude mass into gravity. So that's done. Then we need to see this block's contact, from where this block is in contact with. You'll find there's only one contact at this point, and that contact is with the string. So its string is going to apply a tension force. So you just go to the contact point and see at that point there has to be a tension acting. Now this tension is going to be acting along this string. That means it has to be along this string. So you draw the line, this is along this string. And it has to be pulley first. So that means the string must be pulling it. So you draw just upward direction. This becomes the force of tension. You can call it as a T. So this becomes the diagram that shows forces on M1. That's a simple, right? And you know the point of contact, that's a center point. That's the point where the string is in contact with. Similarly, can we draw this direction or forces or the total forces acting on the block M2? Yes, you can just draw and then match with this. What are the forces that you are going to get? One, non-contact force, gravity, acting at the center vertically downside. So you draw it at m2g, the mass of the block, that is m2 into g. G is a gravity. Then look this block with the contact. First contact point is the only contact point is this of the string. So that's a string. A string means tension, and tension has to be along the string. So vertical and pulling, so upward. Now we have called this string tension as a T at this point. So you will find that this is the same string that's passing over this. At all points the tension remains the same. So you will find this is also going to be same. So this becomes the diagram that shows force for. Similarly, we can say this is the T now. Similarly, we can draw the separate diagram for this pulley. If we draw the separate diagram for this pulley, you will find it's going to look like this. I'm drawing over here the pulley of A part. Now, if you look at this pulley of A part, first of all, you think about the gravitational force or non-contact force, but it is massless. Since it is massless, so no gravitational force, or you can say 0 into z, because mass is 0. Since it is 0, so you are not supposed to show it. Then you need to see the contact of this pulley. Pulley is connected with a string at this point, and that string goes like this. So along this string, and pulley forward. So you call it as a pulley forward. That's going to one tension acting on this pulley. Moreover, this pulley is wrapped with this string. So you can think of this string is massless, which is a massless. It is a part of this pulley. So this will be basically leaving the contact at this point. So this is the terminal points or contact points you can think of. Since they are contact points, and then you need to see at this point what is the direction. This is the direction of this string. So you draw the direction of this string, and this string is pulling, that means it is in this direction. Similarly, at this point along the string and pulling means this. So these are the forces. That means this part of the string has been considered the part of the pulley because it remains in the contact with the pulley. We can easily assume it to be the part of pulley so that it becomes easy for us to show the tension. Here there is no need to show the tension. That means it might come in your brain that what about at this point? Here also a string is. But yes, here one part will be applying tension in this direction, another part in this direction. They will be summing up to 0. That means they becomes internal force. So we do not show the force which are internal. We show force only which are external. So from this point onward, it's not connected with the pulley. So we will treat this as a endpoint. This is endpoint. So these are the tensions. Now this tension is of the part of this string. So this must be T. This must be T. And so this will not be T. We can call it as a T dash. And we can say this is massless. So net force must be balanced. Since net force is balanced, then you're going to write it as a T plus T, that is 2T. And you have used this in case of a constant relation, that if there is a tension T in this string, tension becomes double of it. Okay, and this is the diagram that shows the forces on the pulley. So you are able to draw the forces on the block, forces on the pulley, and what is the rule? You just find first a non-contact force, then find the contact points, write the contact forces. That will be done. Now let's come to the B part. Here it will become more clear to you. And the technique that we are learning, this technique is very important. Later on we will call it as a free body diagram. And this will help us to find out all the forces on any object. Once we are able to find all the forces, then we can easily apply the Newton's law and solve even complicated problems. Well, come to this part, B part, and let's say this is M1 block and this is M2 block. It doesn't matter whether the system is stationary or moving, we need to draw these kind of diagrams. So our interest is to draw diagrams. So let's say we are drawing for this M1 block which is hanging. So you need to draw this M1. Now how much the size of this block you make, that doesn't matter. Even if you want, you can make it as a point size, it's okay, but it has to be made, right? Now, non-contact force, gravitational, it carries mass. Yes, so that's going to be downside. So there's going to be M1 G force acting downside. One thing is done. Then we will see what is the contact points of this block. So this block is having single contact point with this string. So that's going to be upward, and you can call it as a T. Assuming this string carries tension T. So this entire will carry the tension T. So that's become the diagram for M1. Now let's draw the diagram for M2. If you draw the diagram for M2, you will find very similar type, and same process we are going to follow to show all the forces. So here, first of all, non-contact force, this carries mass, yes. So gravity is always there. So it's going to have a non-contact force called mg downside. So you draw this m2g downside. Okay. Then you'll find you need to see the contact of this block. So this block is contact with this platform as well as with this point. So let's see one by one. This point will have this point is connected with a string. So string will have a tension. Tension will be along the string and pulling effort. So you will see this. This is the tension force direction. How much? That's the same amount T, because we have already talked about same string carries same tension. Here there's one more contact point at this ground. So this contact point will also experience another force. Which force? The force that we have understood. That's normal reaction. So here another force has to come. Now this is the common contact surface. So perpendicular, it acts perpendicular. That means ground is going to push this block upward as well. So that will be the normal relation which is perpendicular to the common surface. So perpendicular is going to be along this this direction. And it has to be push. Push means towards the block. Now where to draw? You can draw anywhere on this, or you can draw multiple arrows. It's okay. So we will be catching only one. Or you can draw even like this. That also works. So this is going to be the normal reaction. Normal reaction. Now you see in this M2 normal reaction is coming, not in M1. Why? Because M1 is not in contact with any ground surface, right? It is contact with the string, so string has given its reaction, that is tension, right? So this is the diagram for M2. You got three forces, Acceleration, gravity, tension, all the three forces that we have understood. At least you are able to clearly understood what is the direction of T, what is the direction of gravity, what is the direction of normalization. These are very, very important points. They are very basic as well, but need to be kept in mind for all of the coming questions. Now let's draw this diagram having forces for this pulley. The pulley that is so this is since it is massless, pulleys are massless, so it will not have a gravitational force, non-contact force. And then you need to see the contacts. What are the contacts acting? So the contact has this tension. There's going to be a string. You think like a string till the contact is there. Okay. Then at this point, it will be along the string and pulling. So that's going to be T. Here it is going to be along the string and pulling. That's going to be T. This is how the tensions will be acting on this pulley. Moreover, this pulley is in contact with this rigid support. So this rigid support is also going to give some reactions, normal reactions you can think of. Or we can simply call them reactions. And these reactions will be acting at the center. In which direction it will act, we will be finding it later. Or we can also find over here because we know this is massless. So that means net force must be zero. Net force must be zero. That means there must be a normal reaction acting in this direction. This direction. You can call it as NX. That means normal reaction or reaction acting in the direction of X. Why with this? Because this must be compensating for this. Because net force has to be zero. And if you want net force has to be zero, then X component has to be zero. Similarly, Y component has to be zero. This force already exists. So to compensate it, there has to be a normal reaction acting in this direction. Now, how we are able to decide this normal reaction is simply based on the concept called total force has to be zero. So that means at this point, there will be two types of reactions acting. And these reactions will have their resultant. Where that resultant is going to go? The resultant of reactions will be this. So if you want to show by one force, this is going to be the single force, and you can call this is total reaction. Total reaction. Or you can make the compound. Right. You might also be asked what is this value of normal reaction. Then you can say it's going to be Nx is equal to T. You can solve it, some numerical equations as well. Nx is equal to T. Ny must also be equal to T because net force is zero. So what the normal reaction is going to be? Normal reaction is basically resultant of these two. They are perpendicular components. So you can go for Nx square plus Ny square. Now both are T, so you can write it as T root 2. Many times this question has been asked, what is the reaction? We generally call it as a clamp reaction. Why clamp reaction? Because reaction is coming because of this clamp. This pulley is being clamped at this point. So clamp reaction is going to be T root 2 if it is T, if it is T. That means what is the resultant force of this T and T is? That's going to be T root 2, and this has to be compensated by reaction, that is clamp reaction. I'm just calling it as a normal reaction. You better call it as a clamp reaction. Okay. So point is we are able to draw the diagrams for force, for blocks as well as for pulleys. For that sake, you need to see the contact points. Like for pulley, this was a contact, this was a contact, this was a contact. Similarly, for blocks, there was a contact here, there was a contact here, and the non-contact force. So contact and non-contact, two types of forces are there. You need to think about all, and then you draw all the forces. That's going to be important. Next important contact force is spring force. So let's know some basic about a spring, then the force on that spring. A spring you must have seen and experienced its operations. We show it like this, roughly. And that's called a spring. And when it is relaxed, that means it's free, it's not experiencing any forces. Then whatever this length is called natural length. Generally we denote it by L naught, or you can denote by anything. That's okay. But this is the natural length. So L naught is called natural length. That means it occurs naturally, or you can also call it as a relaxed length. Relaxed length. This is of not much use, but other length that is going to come in, that's going to be important. Now this string is this spring is extensible as well as compressible. So you can extend it, you can compress it, you can do both of it. So let's say you are making this kind of arrangement, you are fixing this one point with a wall and applying a force on the another. So let's apply a force on this. Now you can apply the two type of forces. One is this is going to be compressive force, that is pushing force. You can apply this force, that is going to be elongative or pulling force. Let's say you applied this force. And because of this application, you'll find the spring will have more length than the natural length. So this will get elongated. So it will be some sort of this. Let's say till this point you have elongated. So the force has come to this point. This is the force that you applied. That means this is external force. This is external force. Now you'll find if you remove this force, this spring will not remain as appeared here. It will try to come back to the original position. That means the spring also applies a force on this point. So whatever this point is where you are pulling, that means on you, spring is also applying a force, and that force that is being applied by the spring is opposite to this. How we are able to say this? Because as soon as you remove this, spring comes back. That means spring applies a force like this, which is along the spring, but this time it's pulling. That means this is pulling this point, pulling in nature, or you can say it is towards the original position of the spring. This force we call it as the force of the spring. Okay, so let me remove this thing, and we can show like this. This is the force that is being applied by the spring, and we will call it as a force due to spring. Just I'm writing SP for spring. Okay, and there are assumptions for the spring as well. So we have some assumption. Let me write down those assumptions first. Spring is assumed to be in the beginning level spring. Why we take assumptions, by the way? We take assumptions just because of a reason. We want to make this beginning level learning simplified, right? So to make this beginning level of learning simplified, we take assumption. As we understood the simpler points, then we will go to the more realistic situation. And assumptions mean we are trying to make the situation idealistic, and then we can convert it into realistic situation. Assumptions include like one assumption is spring is massless until unless said to be. Spring is massless. So I'm writing short, it's a massless. We also assume that it is uniform. Uniform means all part of the spring elongate by the same amount. That means it's uniformly stretchable and compressible. There is no other issues coming on this. So generally these two assumptions we carry. Massless is the important one, and uniform all through its natural length, right? That means it can be elongated and compressed. So this situation that has been shown, it is indicating elongated situation. And we can think of this as its natural position, original position. And you can draw this reference line. If you measure this length, this length, let's call it x. And we can be even better way of use better way of measuring. That means we should put the arrow only one side, so that we are sure that we are measuring it from the reference location. So that's called reference location, and it is x, right? So this is gone x length extra, so we call it as x as elongation. So that's called elongation. These are basic points you might be knowing. So elongation is x. It can be written in meter, centimeter, whatsoever. But in calculation, we will prefer to use SI unit, that is meter. Now, in the next situation, if you do this, that means if you apply a compressive force instead of this, that means you applied this force initially. So this will be reaching to this point, and you need to keep apply this force. This is the force that you are applying. Making sense? Now, if you remove this force, you'll find the spring will come back to the original position. So that means spring is also applying a force on the object or the external force. This is force due to spring. Our purpose is to know what is the force due to spring, and then we can use this whenever when the need arises. This is the force that applied by the spring. This is the force that is acting on the spring. This is the external force that is acting on the spring. This is the force that is being applied by the spring. That means if you have a block over here, spring will apply this force on the block. Okay, so that's called force applied by the spring. Now you can see the direction of the force. That is, it is always about this reference location. This reference location is read as a mean position. So we can say direction now. The direction of the spring is always towards the mean position, and it's along the spring, of course, and towards the mean position. You see, when you are elongating it, still it is towards the mean position, and if you're compressing it, still it is towards the mean position. So this is how we will be finding the direction. Here, the let's say measure this point where you have taken this point. You have taken this point in this direction. Now here, if you call this as a x, so this x will be known as compression. So this is the situation for compression. And how much the compression is, you can call it, this compression is x. Understood? So you can compress as well as you can elongate a spring. And once you know this, from here we can determine two important things, or we can conclude basically two things. One about the direction, another thing about the magnitude. Let me talk about the direction and the magnitude. Force FSP. When I'm writing FSP, that means it is force due to spring. Force due to spring. Mind it, it's due to spring. That means it is on the object which is in contact with the spring. Just like block. We will use the block, right? This force acts towards mean position, or you can write direction is towards mean position. Towards mean position, whether it's a compression or elongation in all cases. It might be asked whether it's a pulling effort or pushing effort. Then you say when you are elongated, then it pull up, and when you compress it, then it push, right? So it's both pull as well as pull, both effort. So that's why we are using another term. It's a towards mean position, and mean position is basically the original length that you have talked about earlier. So at that, and of course along, it's always along as well. So along this spring, that's obvious. Next, magnitude. Now you need to remember this magnitude. Magnitude of this spring force is given by FSP, or F only you can write. This is going to be equal to the K into X. X is the elongation or compression. So whatever amount you elongate or compress, that has to be used along with some constant. So K is a constant, where K is called spring constant. Spring constant. This will be given to you, and using this spring constant, X will be given to you. You can get the magnitude. That means spring force has its own formula for magnitude. Unlike the case of the tension, unlike the case of the normal reaction. This is similar to the case of the gravitational force. So it has its own magnitude. Now K is which is a spring constant. It is given to us. It's also called stiffness constant, or stiffness of the spring. And this is a constant basically for a given spring, but it depends on the length. So it is inversely proportional to the length of the spring. This is important point. It is inversely proportional to the length of the spring. So this L is spring length. And when we talk about the spring length, basically we are indicating this natural length, because this X is small enough, so you can reject it. So whatever the length of the spring is given to you, and based on this, you can find. That means if there is a long spring, then K will be less for the same material. It depends on the material as well. So if you elongate as that means if you have a long spring, then the K will be less. If you have a short spring, then K will be more. Then the question will be coming like this: if there is a spring and you cut it, what happens to K? Whether the K changes or not. So if you cut it in two parts, then you'll find the length will become smaller. Since length becomes smaller, then K becomes larger. So it depends on the K, right? And X will be given to you, and from here you can find this. Moreover, if you are looking for the unit of this F, so of this K, so what the unit it is going to carry? You can easily identify the unit because this is a Newton, this is a meter, and this is the unit you are looking for. So it is going to be equal to uh, unit. This is going to be equal to Newton per meter. So Newton per meter is the unit of K. Now, sometimes in textbooks or otherwise, you can also use this, combine these two together because we know how to write vectors in vector format. Here we write magnitude, direction separately. You can combine them together. If you're combining them together, so you can write this FSP, spring force as a vector quantity, is going to be equal to K minus X vector. Can you think of why I'm writing minus X vector? We are writing minus X vector because the direction of force is opposite to the X direction. So whenever there is opposite, you can write as a minus. Here you see X was in this direction, FXP came on this direction. So we write F is equal to K minus X vector. And since we know this is a linear stuff, so for linear stuff you can remove the arrow. That also works, so you can write as a kx. That means here this equation carries both magnitude as well as direction. So this equation carries both magnitude as well as direction. It says magnitude is going to be positive number and direction is going to be opposite to the direction of x. Because k is a scalar number, so direction is coming because of x. Opposite is the force. So this is how you can write the force expression, or you can write the force expression in this manner. Both are correct, right? So this is a very important force that's called a spring force. It's a this is a pulling as well as pushing effort. It's a magnitude you can remember by kx. K will be given to you. K is 1 upon proportional to or reciprocal to L, you can think of. L naught is the natural length. In this case, the length will increase. L naught plus x. Here, L naught minus x. That can be thought of. This situation is called mean position. This mean position. That's also important to remember. Okay. Okay. Now there is a question for you to try. So there is a question. It says a spring of a spring constant K is cut into these two parts, 2:3 ratio. We need to find the spring constant of the smaller spring. There are four options A, B, C, D. You just solve using the property of the spring that you have learned and give the answer in the comment section below. Next lecture you will find the solution of this. Okay, so this is all about this video. In this video lecture you have understood two important forces. One is the tension, another is the spring force, and both are going to play a very important role in our future calculations of Newton's laws of motion. So thank you for watching. Have a great time.